These 5 measurements of a wire all around 0.42 millimeters. They agree closely, which looks reassuring. But then we close the micrometer and it reads 0.02 millimeters instead of 0. They're precise, but they're not accurate. That's a systematic error. It pushes every result in the same direction. Repeating this 20 more times won't remove the error, it only gives us a dependable wrong answer. We need instead to find the cause and correct it. With a 0 error, we check the instrument before starting and subtract the offset. Random errors behave differently. They make repeated readings scatter around the best value because our judgment of the scale can vary. Repeating and taking a mean reduces its effect. That difference makes the rest of the terminology easier to understand. Precision means repeated readings that sit close together. Accuracy means closeness to the true value. Repeatability asks whether the same person using the same method and the same equipment gets similar results. Reproducibility asks whether the agreement survives a change in person, a method, or an equipment. The resolution is the smallest change an instrument can show, so a high resolution does not guarantee accuracy. Now we need to put a sensible range around the measurement. Error is the difference between a measured value and the true value. The true value is normally unknown, so we can't calculate the error. Uncertainty is an estimated range in which we expect the true value to lie. Resolution gives us a starting point. For an analog scale, use half the smallest division. That's often a sensible start. For a digital reading, you start with plus or minus 1 of the last displayed digit. But the method itself can make the uncertainty larger. A stopwatch might display hundredths, but your reaction time might limit the measurements to tenths. If a length comes from 2 ruler positions, both readings contribute, with millimeter divisions plus or minus 0.5 millimeters at each end gives plus or minus 1 millimeter overall. For repeated readings, a common estimate is half the range. If our wire diameters run from 0.39 to 0.41 millimeters, half the range is 0.01. We report 0.40 plus or minus 0.01 millimeters. This is an absolute uncertainty, so it keeps the unit. If you divide it by 0.40, and the fractional uncertainty then becomes 0.025. Multiply 100 and the percentage uncertainty is 2.5%. Fractional and percentage uncertainties have no unit. The uncertainty carries through every calculation. 3 rules cover most A-level questions. When quantities are added or subtracted, you add their uncertainties. When they are multiplied or divided, add their percentage uncertainties. And when a quantity is raised to a power, multiply the percentage uncertainty by the magnitude of that power. The cross-sectional area of our wire depends on its diameter squared. The diameter has 2.5% uncertainty, so the area has 5% uncertainty. The square doubles it, and this is a common exam trap. When a data point has an associated uncertainty, show it with an error bar. One common method is to draw the steepest and shallowest acceptable lines. Half the difference between their gradients estimates the gradient uncertainty, and their intercepts give the intercept uncertainty. Follow the construction the question asks for. Finally, the uncertainty tells you how many digits are actually worth reporting. If a result is 12.5 plus or minus 0.4, writing 12.500 claims unsupported precision. Round the uncertainty sensibly and then quote the value to the same decimal place. So repeat and average to reduce random errors effects, but that does nothing to systematic shifts. Estimate the interval honestly and then carry it through the calculation. Next, we're going to use orders of magnitude to ask whether an answer is even plausible before we start trusting the calculator.